In this lecture, we're going to learn how to evaluate limit, calculate limit. To evaluate the limit, there are all kinds of limit laws that can be found in textbooks. So we're not going to list them here. Instead, we're focused on actually how to evaluate. So there are different ways of evaluating limits, different methods. There's a graphic method. You use graph, try to figure out the limit based on the graph. There's a table method, which is actually very, very useful. Sometimes if no other way would work out, you do the table. You create a table of values to try to figure out limit. But here in this video, we'll focus on the algebraic method, which is very common, and this our focus too. We usually do it this way. All right, so the algebraic method works like, say, if you want to find the limit, you always try to just plug in the value, all right? So, for example, want to find the limit of 4x squared minus x when x approaches 2, we just plug in 2 for x. The theory goes like, if you can plug in, you find the limit. If you cannot plug in, well, then we'll talk about that too, all right? So let's just say when we can plug in and how to get the answer. Or just like I said, pretty simple. This limit, x approaches 2, we plug in 2 for x. So 2 for x, this is 2 squared, that's 4. 4 times 4 is 16. 16 minus 2 is 14. So that's just how you get the limit. You just plug in. 4 times x squared, no, x is replaced by 2, right? X is replaced by 2, so you figure out the answer is 14. So that's a limit. So this is a direct approach. Just plug in. Let's see another one. X approaches 3. So again, we just plug in 3 for x. 3 for x. Work it out, simplify. So limit is 7 over 2. Just how it works out, okay? Assuming you can actually plug in, you can actually evaluate. Now, let's look at the more examples. So here, for example, in this limit, I have a function, x squared minus 4 divided by x minus 2. When x approaches 2, this time though, cannot plug in 2 for x because the denominator becomes 0. So, well, sometimes if we cannot plug in directly, right, we can do the table method. We can create a table, check out the left side limit, the right side limit, and figure out that way, right? But here we're talking about the algebraic approach. So let's do it algebraically. It may or may not work out, all right? But how we do it? We're going to apply what's called factoring method, factoring technique. We're going to apply factoring technique. Okay, factoring technique. Now, how this method works out is whenever expression becomes 0 for some value, right? It means the x minus 2 is definitely a factor of that expression. This is because of unimportant result in algebra. So if an expression becomes 0, there's a 0 factor. Okay, so we're talking about zero factor or troublemaker or trouble factor. All right. So in this limit, when x goes to 2, this becomes 0, right? So x minus 2 is a trouble factor. And for that matter, when x goes to 2, this becomes 0 too. 2 squared minus 4 is 0. So it's guaranteed. X minus 2 is a trouble factor contained in this expression. Okay, so again, it's good to keep this in mind. So we have a target. We have this bad guy to go after. All right. So anyway, so how would this factorial method works? Well, x goes to 2, cannot plug in. X minus 2 becomes 0, right? And as a matter of fact, x minus 2 is a trouble factor. So the whole point is to try to get rid of this trouble factor, bad guy, by factoring and cancellation. All right, so this is why it's called a factoring technique. So we try to factor, try to simplify. If now we don't know what we'll get, we'll just try to factor. For example, we factor x squared minus 4 on the top. In algebra, it's pretty simple. There's a formula. So we have x plus 2, x minus 2. Factoring, very simple binomial x squared minus 4 to factor, right? The bottom x minus 2 is first order. You can never factor further reduce or factor first order polynomial. So we'll just copy it down. As a matter of fact, we can already see troublemaker on both the top and the bottom. See, this is troublemaker and same troublemaker. Nice. So we just cross out. Gone. The limit becomes just that. Troublemaker is gone. This time we try the direct approach. Plug in 2 for x. Nothing will go wrong. Just plug in. The answer is 4. 2 plus 2 is 4. Replace the x by 2. So we have 2 plus 2, 4. Let's get the answer. So this is how this factoring method works. You try to factor. So do some algebra. Let's see another example. X goes to negative 5, right? We're going to see the limit of this fraction. Again, if you plug in negative 5 for x, denominator becomes 0. All right, cannot directly plug in, so we're going to try to factor to simplify. Idea is to simplify, to factor the top, factor the bottom, and hopefully we can cross out troublemaker. Now, x goes to negative 5. In other words, when negative 5 is plugging for x, this becomes 0, denominator becomes 0, numerator becomes 0 too. So we know x minus negative 5 would be a troublemaker, bad guy. So it'd be x plus 5. Let's see if we're going to be able to expose this bad guy through factoring, and then cross out, of course, right? Okay. Let's see how we factor. So the main thing is to factor, right? Bottom is simple. Bottom x squared minus 25, there's a simple formula. So it's going to be x plus 5, x minus 5. You see the bad guy here? Oh no, I'm sorry. It's this time. It's this guy here. Okay, and I'm sure if we factor the numerator, we're going to see this bad guy too. Well, let's see. How do we even factor, right? numerator is trinomial. So how do we factor the trinomial? There are different methods. The method I use is cross product method. So let me explain to you how it works. So I analyze the coefficients. Okay, first of all, coefficient of x squared is 2. So I come up with two numbers whose product is 2. Then I check out the constant, which is 5. Then again, I try to find two numbers whose product is 5. The first thing that comes to my mind is 5 and 1. All right, 5 times 1 is 5. Now, will this work? How do we get the correct layout, numbers, arrangement, right? Well, I do modification along these diagonal lines, cross product. So I do 2 times 1, I do 1 times 5. So 2 times 1 is 2, 1 times 5 is 5. So it's 2 and 5, those two products, right? With the 2 and the 5, I'm asking myself, can I get the 9 in the middle? No way. Well, of course, you try to do addition, subtraction only, right? So again, you have 2 and 5. With 2 and 5, with addition or subtraction, there's no way we can get the 9. But that means this arrangement is not correct. So we arrange it differently. We arrange it as 1 and 5. So let's do 1 and 5. Try again. So this time, similarly, let's do cross product. 2 times 5 is 10. 1 times 1 is 1. With, same question, with 10 and 1, can we possibly get 9? The answer is yes. We can do subtraction, right? 10 minus 1 will be 9. So that means it's possible. So sometimes even you try this, it will not work. Maybe you should try different combination. For 5, there's only one combination, 1, 5, right? You should rearrange it as a different order as a 5, 1. But the different number, you may have a different even combination of numbers. Say if this was 20, then that would be complicated. You could try 5 and 4, 2 ways, 5, 4, 4, 5, or 2, 10, 10, 2. So it can be more complicated, but you get the idea, You just have to try whatever that works. Keep trying until you find, something that works, some combination, the right arrangement that works. Okay, in our case, we see hope here. 2, 5 is 10, 1, 1 is 1, so 10, 1 will give me 9 if I do subtraction. As a matter of fact, do subtraction to get exactly the positive 9, 1 times 1 has to be negative. So this just tells me I have to have a negative 1 here. As a matter of fact, one of those two got to be negative anyway. See, this was actually negative 5, right? I mean, we focus on the number, then try to fix sign, like in this case. That's how it works, okay? So this works out just perfectly. Let's check again. 2 times 1 is 2. Negative 1 times 5 is perfectly negative 5, and that's what we want to match. Plus, do cross product. 2 times 5 is 10. 1 times negative 1 is negative 1. So 10 plus negative 1 is precisely 9. Everything matches. So we just hit the right combination, the right layout. What it means is we have factoring. So the numerator can be factored as, according to my numbers, be 2x minus 1. Pick up the 2 here. Pick up a negative 1. So it'll be 2x minus 1 times 1x plus 5. 1x plus 5. And we see the trouble factor there. We see the same trouble factor there. Cross out. We'll use black. So -5. It's hard to write. Okay, x versus -5. So I cross out the trouble factor. The top becomes 2x minus 1. Bottom becomes -x minus 5. This time, try to plug in directly, see if we can find out the limit by simply evaluating the expression. So there's no problem. When we plug in -5 for x, top becomes -11. 2 times 5, 10. 10 actually is negative because it's -11. Bottom is -10, so it becomes -11 over -10, or 11 over 10. So this is how we try to apply the factoring technique to get rid of troublemaker. It's because in the beginning, when we started out and tried to plug into directly, we could not, because denominator becomes 0. Denominator becomes 0. Actually, we can tell x minus 3 is trouble factor. Through factoring, we cross out the same factor from top and the bottom, and then eventually we were able to plug into directly to find the limit. Similarly here too, when we try to plug in -5 for x, the number becomes 0, then we factor and expose the trouble factor top and the bottom to cross out, then we're able to just plug in -5 directly to find the limit. So this is to eliminate trouble factor through factoring. Now there's another method or technique we utilize to get rid of the troublemaker. It's called rationalization. All right, let's look at the limit here. X goes to 9. Well, the denominator becomes 0. Now we don't even need to worry about the numerator for now. Okay, just check the denominator. So 9 plugging for x. This is a square root of 9 is 3. 3 minus 3 is 0. Trouble. Now this time we're going to try to rationalize the denominator. Factoring will not work because factoring can only be applied when you have second order or higher order polynomials. This is radical. This is first order, so we don't talk about the factoring, with the radical, and it's impossible to factor first order. We don't try to factor first order, never. Anyway, so we use this different method. It's called rationalization. How it works is, well, before I get to that, again, keep this in mind too. Whether it's numerator or denominator, when we plug in 9 for x and it becomes 0, it just means eventually somehow x minus 9, well, x minus 9 is definitely the troublemaker, and somehow we were going to be able to show this troublemaker x minus 9 can be exposed. So this x minus 9, you'll see, can be exposed actually through rationalization. That's what we're trying to achieve. All right. So how do we rationalize? We multiply the conjugate of the radical expression. So the conjugate of 3 minus square x is 3 plus. It's always plus minus conjugate of each other, right? If you have a minus involving radical, conjugate is plus. If you have a plus, the conjugate of that expression is minus. So we multiply top and bottom by the conjugate. Bottom, now the top. Again, by the same thing, right? Algebraically, we have to do this. Cannot just multiply bottom, okay? So when we multiply the bottom, by 3 plus square x, we actually multiply it out. So the conjugate part, we actually multiply it out, right? So the bottom, so that's the part we try to rationalize. The original 3 minus 3 square x is the part we are trying to rationalize, so we multiply it out. It's a 3 minus times 3 plus. There's a formula. A minus B times A plus B. There's a simple formula. AB, let me write down here. It'd be 3 square minus square x square. All right. So it becomes simply 3 minus x. No more radical. Rationalized. All right. Then top. Okay. Here's key. The top we don't actually multiply out. Oh, it'd be 9, I'm sorry. 9 minus x. The top we actually don't multiply out. The reason is, well, first of all, our focus is to rationalize 3 minus square root of x only. Once we get the what we want to achieve, right? 9 minus x, that's good enough. The top, we don't need to rationalize anything. As a matter of fact, we should not multiply out. The reason is, again, remember this is a troublemaker we talked about, right? X minus 9 is troublemaker, or 9 minus x, same thing, just a reverse order. You know, that's becoming 0. So we already see 9 minus x on the bottom, which is a troublemaker. The top, in the form of a product, we see the troublemaker 9 minus x, right? Clearly exposed. Let me write it down just to explain. All right, we already see the 9 minus here, visible. If you multiply it out, you can make it disappear. If you make it disappear, then how can you cross that out, right? So do not multiply out. So there's troublemaker, there's the same troublemaker, you cross out, right? Don't make it the top 9 minus x disappear by multiplying out. You don't multiply out. Okay, cross out, troublemaker is gone, 9 minus x, x minus 9, basically the same thing, with the difference of factor of -1, right? But anyway, nothing will become 0 in the denominator. The denominator is key, okay? So we can then directly plug in 9 for x, 3 plus square root of 9, so 3 plus 3, which is 6, and that's the limit. All right, so this is an example where we rationalize the denominator to get rid of the troublemaker. Eventually, we can plug in, find the limit, right? So this is how rationalization technique works. Let's see one more example. So here, we try to find the limit of 2 minus x divided by whatever here, right? It's radical. We're going to do rationalization, obviously. Of course, the main reason is denominator becomes 0. So you can see if you plug in 2 for x, this is square root of 4, which is 2. 2 minus 2 is 0. Of course, that you see 2 minus x on the top too. That becomes 0 too. So anyway, the key is to rationalize. How? Multiply by the conjugate. So the expression we try to rationalize is minus, right? So we're going to multiply by plus. Times plus 2. Of course, to be correct, we have to, at the same time, multiply the top by the same exact thing. So mathematically, algebraically, we're not really changing anything. This, except its appearance. So this is exactly this, because you can always cross out if you change your mind. All right, so now let's see what happens. What happens is, again, when the radical we try to rationalize is multiplied by its conjugate, we use the same formula to try to get rid of the radical. So it becomes the product. So it becomes square root of x plus 2 squared minus 2 squared. Oh, I think I made a mistake. Oh, wait, let me see. Oh, there's nothing wrong. Let's see. Okay, so anyway, let's continue. No, I thought. Oh, so this will become x plus 2 minus 4, x minus 2. All right. So the bottom becomes x minus 2. Okay. Now, we don't actually see x minus 2 on the top. We rather see 2 minus x. But algebraically, 2 minus x and x minus 2 are same kind of a bad guy. So what we do basically is to factor out the negative 1 from those two terms in the parentheses. And you're going to see x minus 2. So let's factor first. So factor out negative 2 becomes a negative 2, negative x becomes a positive x, so it's basically x minus 2. All right. Now, I want to point out though, we multiply the denominator out because we try to rationalize the denominator, original denominator. Well, in the numerator, we cannot multiply this out. Okay, if we multiply this out, the 2 minus x is gone. We will not be able to expose the x minus 2. Okay, you have to keep this visible and factor out negative and expose clearly this bad guy. X minus 2, x minus 2. And cross out. Okay, there's a still negative sign in the front. This time, x minus 2 is gone. Where's my, oh, here's my 2. That's ugly. All right, so x approaches 2. This time, plug in directly. Radical becomes square root of 2 plus 2 is 4. Square root of 4 is 2. 2 plus 2 is negative 4. So we find the limit to be negative 4. Again, in this example, we apply the rationalization technique to, basically expose the troublemaker from the top, from the bottom, to cross out in order to find limit. All right, so we stopped here.